Hey everyone, welcome to another paper review. Here today, I'm going to be talking about the elastic weight consolidation idea that I introduced in the previous paper review. This idea was presented in the proceedings for the National Academy of Sciences 2017, titled "Overcoming Catastrophic Forgetting in Neural Networks," written by James Kirkpatrick et al. A collaboration between DeepMind London and the Imperial College of London. So let me just dive right in. So continuing our trend in learning about the field of lifelong learning, we previously looked at the problem of continual learning, where we are concerned about the model's ability to learn a new task n, given that we have already learned on previous n minus one tasks. And a big issue in this field is catastrophic forgetting, where we are concerned about the model's ability to remember the previous n minus tasks that we have already learned, given that we are training on new task n. While training on the new task n, there is interference between the representations that's needed to learn about the new task. And because of this interference, you essentially start forgetting about what you learned on the previous n minus one tasks. And hence you encounter what's known as catastrophic forgetting. And it's a big issue, and we've been looking at papers that try to tackle this problem. And today we're going to be talking about a regularizer, essentially a loss term that's to be added to neural network models. The loss term is inspired from a lot of biological neural models. So let's look into, I like to focus on the notions and the ideas of what the authors want to say in the paper. So that's the weightage that I give, and less weightage on results. Today, actually, I'm not going to be talking about the results at all. It can be read in the paper. At the time, it achieved state-of-the-art results on the MNIST permuted task, the CFAR 100 class task, and also in reinforcement learning. They've found that it achieves state-of-the-art for the Atari games, etc. I'm not going to talk about the results because it can be read in the paper. So let's dive right into the notions that the authors had initially before coming up with this paper. So some of the important notions that and papers that the author cite is mainly Yang et al. 2009, where essentially they did a study and they found that mammalian brains have mechanisms to avoid catastrophic forgetting by protecting the previously acquired knowledge in neocortical circuits. And especially in Yang et al., they did the study on mice, and they found that whenever the mouse learned about a new task, once it has learned that task, it will it created enlarged dendritic spines. So dendrites are these nodes that come out of neurons, and essentially they found that these dendrites enlarged and formed like a spiny shape on those neurons. And what this does is sort of make the neurons resistant to being changed in the future. So they found that these enlarged dendritic spines persist for subsequent period even after learning what it is, and it's sort of accounted for retention of performance. And also a subsequent study by both Hayashi, Tagaki, and Shikon and et al. Subsequent study found that when you erase those spines, you remove those spines, and then allow the mouse to learn about new tasks, they found that the corresponding skill is forgotten faster. Interesting, very. So essentially, there are these dendritic spines that help you preserve these memory retention, preserve those learned tasks. So essentially, it seems like the takeaway that author has is that continual learning in mammalian neocortex relies on task-specific synaptic consolidation. So that's where the term synaptic consolidation comes from, where you have these neurons that get consolidated after they've learned about a particular task. And essentially these consolidations render those neurons to be less plastic towards being affected in the future to learn about when you're learning about newer tasks. So interesting and interesting ideas, and that's more inspired from biology, a theme that we see continuously in this field. So the biggest takeaway is that when you're training a standard fixed neural network architecture, and you're training on sequentially on multiple tasks to gain mastery on all those tasks, you're less susceptible towards catastrophic forgetting if you consolidate important weights that you've learned for the previous task and make them less susceptible towards change. So you want to make them less plastic towards change. So how are you going to do that? The authors call their method as elastic weight consolidation. In essence, let me just highlight what the problem is. So for theta being the weight parameters you're learning, the weight of the neural network for which you're learning the best parameters to represent the tasks. So let's say you essentially you want to train those weights such that they do really well on task A and task B. So there are two tasks. Now you see that task A, the best error or the best fit for the model is obtained when theta A is in this region. So when theta, the parameter, is in this region. And the best error for task B is obtained when the theta parameter is going to be, the parameters of the model are going to be within this region in the loss landscape, the weight landscape. Now, so when you learn, so let's say you start training the model for just task A. So you're doing sequential mastery of tasks. So you train on task A. And now you get to theta star A, where the model has been trained and you achieve a minima, and that's theta star A at this point. Now, when you start learning about task B, and you do not penalize how the weights are going to transition, there's no penalty, then essentially it's going to take the path of least resistance and the most easiest path, which is shown in blue, and it's going to go to theta star A to theta, say, star B, and this point over here. Now, when you query on A, obviously it's going to have a higher error than this region. So it's not the most optimal solution for A, as you can see. Now, a simple idea that you can come up with is say that I want the thetas, essentially the weights that I've learned for A to be as close to A as possible when I'm learning for B. So I'm essentially just penalizing how much change of weight happens from theta star A to say theta star B. So that's shown in green. So essentially what that constitutes is an L2 penalty on how much the weight is being changed. So you take the weight parameters, you look at the value differences between while training, and you want to penalize how much it's changing from the initial value that you had. Now that might be a viable idea, but you find that when you do that, it's so restrictive that your model actually learns nothing and it steps off into this green path, and you start doing less well on theta A, on the task A, and you actually don't learn anything that's useful about task B. Now, what the authors propose is a more softer way of penalizing the change in weights, and by doing this softer way of penalizing, they hope that you take the red path here, where the ideal path, where your trade-off, where you're doing really well on both task A and task B. There might be a slight trade-off on performing on task A and slight trade-offs on performing on task B, but overall, this is the best set of weights to do well for both task A and task B. And how do you do this soft consolidation? So that's what we want to learn, and I usually go into the math of what the authors want to do, so that there's no like hidden mystery. So there are like 4 math equations here. I'm just going to go into the math, scary big values, but nothing to be afraid of. I'm just going to dissect these terms and what they're trying to say essentially by using these math. So essentially, if you have a data distribution that you have essentially your data set D, and given that you have a model which has set of weights theta, all that you're concerned about as in your life is what is the best theta that would fit the data. So essentially, all you're concerned about is the likelihood that a given theta is the best fit given the data distribution. Now, one can go ahead and apply Bayes' rule and flip this on the other side. You can ask the question, okay, what data distribution, what is the best data distribution that would actually fit the given theta that I have? Okay, and then, so you're essentially querying your theta and asking, hey, what is the best distribution, data distribution that actually you're representing? So that is, you get this D, and then plus the prior of the weights itself, and then compensating for the distribution, the prior of the distribution of the data itself. So if you look at essentially this term, this is nothing but your loss function that you're doing. So you're essentially querying every time when you're training, hey, you're this model, you have learned something theta, what is your distribution? You look at the output, and now you have like a loss term based on which you're say correcting those theta values. So you're doing gradient descent, but essentially this is nothing but the loss term. So keeping that in mind, what we are concerned about in this problem is we're concerned about fitting to a distribution task, fitting to the new task B, given that we have already trained on task A. So we are right now just simplifying the problem. We are concerned about two-task learning, so not like overall multitask learning. There's just two tasks, task A and task B. Now, task A has a data distribution dA, and task B has a data distribution dB, and together they combine to give the entire data distribution D. So essentially, now more mathematical terms, but what the authors show is that if you just plug in the previously described terms into the previous equation that I showed in the previous slide, you get this. And all you're doing is you're still finding which theta best represents the given data distribution. Here, the data distribution is still over the entire data. We are still concerned about which theta represents both dA and dB, which dA plus dB gives you D. So essentially, this is still the best theta that represents the entire data distribution. But now you can plug in that we are already trained on dA, and now we are training for dB. So now your loss function is essentially just the loss function that you have for training dB on dB. So you want the theta to best fit to dB based on the loss function for that task. And now your theta, we talked about prior theta here, which is the distribution of your theta from which you sample. Typically, if you looked at literature, you would do like you're initializing your weights. You do random sampling sometimes. You do Gaussian distribution sampling. You might do something like normalized sampling, but usually you have distribution from which you're sampling this theta. But in this case, we are considering the scenario where we have already trained on task A. So now this prior that we talked about is now actually a posterior, where you're concerned about what theta best represents dA. So you have already trained your model such that it's it has fit on this data set dA, and we were saying that this is the best model, or somewhat the best model that represents dA. So you already have this, so it's a posterior distribution, and now you have to compensate for the data set distribution, which you usually don't care because it's IAD. Now, this two math equations, why is it there? Essentially, what is the argument here is that we are really concerned about this. So you have fit your model for the previous task dA, and now you have the theta is now a posterior distribution. Now, when you're learning about dB, you need to consider that the posterior distribution has some information on which weights are important, and we have to use that information. So let's say you peek into this posterior distribution, and we get the final loss function. So let's say you peek into the posterior distribution that I showed here, and someone tells you, an oracle tells you that oracle gives you like F5, and F5 is nothing but the Fisher information matrix. I'll get into that quite soon. But the oracle tells you that, oh, these weights are this much important, and these weights are not important. And if you have those scores for the weights, now you can essentially do the same L2 error penalty, but now it's a weighted sum where the weights are given by score of how much the particular weight value is important. So essentially, you're minimizing your loss function to minimize for learning about task B should have an additional loss term, additional penalty that minimizes the difference between the new theta that you're learning and the old theta A. But this is a weighted difference that where there are penalties more for weights that are more important. So you don't want to change them. And there is less penalty for weights that are deemed not important. And the importance value are found using the Fisher information matrix. And also lambda is a parameter that tells you how much weightage should be given for the old task. So what is this Fisher information matrix? I'm going to link a couple of videos from YouTube that describes about what Fisher information matrix is, and does a really good job in explaining it. And here, what I want to do is tell you why Fisher information matrix is used in this case. So let's think about the general problem of training, and you have like a huge loss landscape. That's the loss landscape is generally high dimensional, but we are visualizing it in 3-dimensional space here. So this is like sort of you can imagine to be a loss landscape for a particular function you're trying to learn. And generally, you have weights that you randomly initialize, and that's considered here in the red ball here. And while training, you move the ball, and the ball is moved by gradient descent. And you move the ball, and you move it around, and you find a local minima. In this case, I think the global minima. And so you train this model to learn a good representation about, say, a task A. And you get this ball here. And this ball is the theta star, which is sort of like the local or global minimum that you've learned that after training on task A. Now you want to understand that there are in theta star, which is sort of the best weight representation to learn about task A. Now it consists of individual weights, say K parameters that consist of that is present inside theta star. Now, essentially, you want to identify what theta star K are important, which of them are important, which are not. And one way you can do that is, say, perturb the weights. So essentially, if I find the curvature, or in layman terms, I'm finding the double differentiation of the loss landscape with respect to the weights. So what I'm doing is I am moving one particular weight, let's say WK or theta K star, and from this position, I'm moving it ever so slightly, and I want to identify how much by just moving one weight do I change in the loss landscape. So I'm finding the curvature in the loss landscape by which the weight change, by changing this one weight, how much in the loss landscape do I change? So if I move out pretty large, like if there's a large difference, that means those weights are important. And there are going to be some weights that do not affect the change, like in the landscape, you do not change that much. So there are some weights that you're not actually changing a lot. So those weights are deemed as non-important. And so how do you find the double differentiation? It's essentially, that's what the Fisher information matrix is giving you. The Fisher information matrix is giving you the double differentiation of the curve and given the set of weights. So it's telling you how much this weights tell you about that particular local minima or the global minima. And there is neat tricks by which you can compute the Fisher matrix efficiently. So you do not need to do double differentiation. You can just get it from single differentiation. And you just look at the diagonal values of that matrix, and that tells you the weightage of each of those weight parameters. And now that's how we find it. So that's the most important, I think, mathematical idea behind this, using the Fisher information matrix. Essentially, you're looking at the gradient for that particular location to see the curvature of when you move the ball. So by seeing how much it's affected for each of those weights, you can tell how important that weight is, and that's the intuition. And using that is all you need to weight the weights during the penalization and loss term. And yeah, that's it. That's it for this paper review. And by doing this, they get a lot of good results. So I would ask you to go and check out the paper and let me know your thoughts. Thank you.